Let's solve for x. We have some logarithmic equations here. And the first thing you want to do for any log expression, if you see a variable, make sure you check the domain of this function here. That's log base 3 of x. And we already know that x is greater than 0 according to the definition of a logarithm. If you've forgotten, you might want to write it. B to the y power is equal to x if and only if, a double-sided arrow, if and only if y is equal to log base b of x, where y is actually a function and the base is not equal to 1, the base is greater than 0, and this is the most important part. Your domain of that function is x greater than 0. In other words, it's going from 0 to infinity. So in our case here, we have log base 3 of x. We need to indicate that x is greater than 0. For this particular problem, it works out to be pretty straightforward. Using the definition of log, we're going to read it this way now. We're going to read it as the base to an exponent is equal to x. So the base is 3 to the exponent, which is negative 4, and that has to equal x. So maybe I'll highlight it here. So base to the exponent is now equal to x. So that is the pattern. And notice we are starting with the log equation and we're switching it back to an exponential equation with an indication of your domain. In other words, the log of your inputs have to be greater than 0. Well, we got to make sure x here is a positive number. Well, of course it is. You've seen this before. 3 to the opposite of 4 just means 1 over 3 to the 4th. And that is now equal to x. And of course, x is equal to 1 over 81. Notice with equations, every single line of your work is an equation. When you're solving equations, you write nothing but equations. This one here, same thing. We got to first indicate that the domain, the log of any input, has to be positive. So x has to be greater than 0. Now we'll use the definition of a logarithm. We're going to say base 64 to the 1/2 power is now equal to x. Now that's an expression. 64 to the 1/2 power is really, that is just 8, right? That expression is the square root of 64, which is equal to x. And of course, x is now equal to 8. Let's do part C. Notice this time we have the input. The input is called 2. So we're just going to use the definition of log here. The base here is x. So we're going to write the base is x raised to the exponent. And that is now equal to 2. Now how do you solve for x? That's the 5th root of x. In order to get x, we're going to apply the function x to the 5th power to both sides. So what do we have now? We have x on the left-hand side of the equation, and that is equal to 32. So far, remember, if you're solving an equation, every line of your work is an equation. Solving an equation, every line of your work is an equation. Here's an inequality. I have to admit, that is because I just wanted to indicate the domain. But look at part C. If you have an equation, every line of your work is an equation. Same thing here. If you have an equation, the next line of your work has to be an equation. We have the input to be 1 over 81. Our base is x. And we're going to raise that to the 2nd power, and we're going to set that equal to 1 over 81 by the definition of a logarithm. So how do we solve a quadratic? Well, there's a couple different ways. Quadratic, usually you set it equal to 0. So x squared minus 1 over 81 is equal to 0. And so we factor. Difference of two squares. So x plus 1/9 and x minus 1/9 is equal to 0. So x equals 1/9, or what? X equals -1/9. Now, by the definition of log, our base has to be what? Our base has to be greater than 0 as well. The base x, so base x has to be greater than 0. I could indicate it right here. And notice I'm talking about the base x. So I'm really talking about this. The base b has to be greater than 0. Okay, if you're looking to the top upper left-hand corner, top upper right-hand corner of the screen, the base has to be greater than 0 as well. So here our base was called x. It's still the base. And so which one is not an answer? X equals -1/9 is not the answer. So I'm going to lightly cross that out. Just lightly. And so final answer here is x equals 1/9. Now, even though you got your final answer, I'm going to circle the final answer, but the work is really important. All this work has to be here. Don't skip any of those steps. All that work has to be here. I am going to show you an alternative way to do part D. So I'm going to show you another way to do part D. I'm going to start over. We have log base x of the input, which is 1/81, is now equal to 2. There are invisible parentheses there. That's why we call it a function. It's an input. You're looking at the input there. There's always been invisible parentheses there. So we could have the base is x, raised to the second power, is equal to 1/81. Some people might take the square root of both sides, and the square root function, though, usually causes some complications. The square root of x squared, by definition, is actually the absolute value of x. So the absolute value of x is now equal to what? Equal to 1/9. But how do we solve an absolute value equation? We have two cases. X equals 1/9, or x equals -1/9. And notice we're back at the same spot. We're once again, we're at the point where base x has to be what? Greater than 0. And so that leads you to lightly cross this one out. And then we have x is finally equal to 1/9. And I could circle that as the final answer. However, once again, all this work needs to be here. So if you're solving this equation with a different method, all your work needs to be shown as well. Just like any of these problems here, all your work here has to be shown. All your work has to be shown. All your work has to be shown. So make sure you're showing your work very neatly and organized so that it leads you to the final answer. Use the properties of logarithms to expand the following expression. Log of the argument that contains 6 times the quantity x plus 4 raised to the third power, all over the square root of x to the fifth power. First thing you want to do, if you haven't already, memorize all the properties, or at least written all the properties of logarithms on a sheet of paper. What we're first going to do is look at this as the log of a division expression, okay, or a log of m over n. And if you take a log of m over n, we're going to write that as a difference of logs. So log of bracket 6 times x plus 4 raised to the third power minus log, let's say x to the 5/2 power. Now we're going to read this from left to right, and notice we have a log of a product. And if we have a log of a product, we also have a property that says we can write that as a log of 6 plus the log of x plus 4 raised to the third power minus log base 10 x to the 5/2 power. Only one step left. You do have another log property that says you could take that exponent and move it to the front of the logarithm to represent a coefficient. And there you go. You have manipulated the original expression to be expanded as wide as possible. Go ahead and circle your final expression. And let's try the second example here. We have an expression here that we would like to write this as an expansion of as many logarithms as possible. We'll start off with writing the square root symbol into a power. So I'm going to write this as parentheses x plus 6 raised to the 1/2 power. And inside those parentheses is x plus 6 quantity cubed over x to the 5th. What are we going to do now? We're going to bring that 1/2 to the front. And we have a log of x plus 6 raised to the 3rd over x to the 5th. And now this looks like the other problem in part A. The log of a division problem is going to be a difference of logs. Log of x plus 6 raised to the 3rd minus log of x to the 5th. And then finally, one more step here. We could have 1/2 times 3 times the log of x plus 6 minus 5 times the log of x. And there is our final expression. It is expanded as much as possible. I'm going to go ahead and circle our final expression here. Solving a multi-step equation involving natural logarithms. Solve for x. 6 minus 5 times the natural log of x is equal to 8. Well, intuitively, you would actually subtract 6 to balance the equation. We're trying to isolate the variable. In this case, the variable looks like a function. Our function is the natural log of x. So it'll be nice to get the natural log of x by itself. So far we have what? We have -5 times the natural log of x is now equal to 2. Once again, we would like to get the function by itself. So let's divide the entire sides by -5 because -5 is not 0. Once again, we do have the function by itself. And in fact, that function is equal to 2 over -5. By definition of log, we know what x has to be. X has to be e to the -2/5. And you're done. If you want to, you could write your answer as positive exponents. So that would be 1 over e to the 2/5. So this is what we call in mathematics an exact answer. Some of you might even write it like this. X equals 1 over the 5th root of e squared. So these are all pretty answers. So whenever you're trying to solve for x, do try to write an exact answer. So there's could be multiple forms. This is an exact answer. This is an exact answer. So what would a rounded answer be? Well, let's find out. Why don't we round our answer to the nearest hundredth? Round to the nearest hundredth. So make sure you could find E on your calculator. And you could even try to type this in your calculator. You can call this calculator friendly. Let's find out what X is. So X is this long decimal and there's 3 dots after it, indicating that this decimal never stops. Now we want to round this to the nearest hundredth. So we're going to look in the thousandths place. The thousandths place is 0, which is less than 5. So we're going to go ahead and round this number. X is approximately, rounding down to 67 hundredths. So let's recap here. First, show your work, balance the equations, show your answer as 2 equations. Notice we have 2 exact answers here. And if you need to approximate, go ahead and type a calculator-friendly instance. Actually, they're all calculator-friendly. You just got to make sure you know how to use your calculator. And you should get X is approximately 67 hundredths if you decide to round to the nearest hundredth. I am not going to circle this answer because it's not exact. I actually want the exact answers first. So when you're solving equations involving logarithms, definitely find the exact answer first. Always show this first before you attempt to round. Let's solve some equations. Both these equations here have logarithmic functions in them, and we have to pay close attention to the domains. So here's a log function, and here's a log function. The first one here says that x minus 3 has to be greater than 0. So x has to be greater than 3. And the second one here says that x must be what? Greater than 6. And that's by definition of a logarithmic function. So our domain is what? X has to be greater than 3 and x has to be greater than 6. So where do those x values overlap? They overlap here. So I am going to circle this. Even though it's not an answer, I'm going to label this triple star because we're going to need that. We need our x values to be greater than 6 only. All right. So typically when we're solving equations, we would like to isolate the variable or isolate a function by itself. So in order to do that, let's try to group these log functions together somehow. And maybe we could get a single log function on one side of the equation. Let's add the log base 4 of x minus 6 to both sides of the equation. And if you do that, you should get log base 4 of the quantity x minus 6 minus log base 4 of the quantity x minus 3 is now equal to 1. And we react to these problems because you've memorized the log properties or you're in the process of memorizing them. So the difference of a log function with a common base is really the log of the fraction. What did I just say? Well, let's just write it symbolically. This is the log of x minus 6 over x minus 3. And that is now equal to 1. We already know x can't be 3. That was indicated a while back. I'm just noting it again because of habit of inspecting the denominator. Now, by definition of log, we know that 4 to the first power is now equal to this rational function on your right. What is the rational function? Is equal to x minus 6 over x minus 3. And of course, we could do fraction busters and clear the fractions, and we get a nice linear equation now. What do we get? We get 3x is now equal to 6. And we get x is equal to 2. Well, darn it. But triple star says what? Triple star up there says x has to be greater than 6. That was given from the very, very beginning. In other words, this is yielding an extraneous number. All this work is necessary, but more importantly, you noted that x is greater than 6. So logically, what do we conclude? We conclude that there is no solution. Now, even though I'm circling the final answer to be no solution, you must provide all this evidence to make that conclusion. So yes, we have a final answer, but your work is very, very important. So make sure you show your work, show your evidence, show your procedures. It's really about the work in mathematics. Second example. Once again, we would like to isolate the logarithmic function on one side of the equation. We'll start off very, very similar. We're going to add log base 2 of x minus 7 to both sides of the equation. Why do we want to do that? So we get another equation. We get a new equation, and that new equation is now going to be log base 2 of this. The sum of two logs with the common base is really the log of the product of the arguments. So it's going to be this. And then what's on the right-hand side of the equation is just equal to 3. Now, by definition of log, we got 2 to the third power. And of course, you know what that is. That's 8. Is going to equal the argument. What is the argument? It's x squared minus 12x plus 35. Now, I got a little pencil happy, and I forgot to spot the domain. I still remember, though. I do need to know that x is greater than 5, and x has to be greater than 7. So where do those two overlap? That means x must have to be greater than 7. And I'm going to call this triple star. Here, why don't I call it quadruple star, since I used triple star in part A. And I'm going to circle that. We need to know that x has to be greater than 7. Back to the equation down here. How do we solve quadratics? Well, you react to them. You study them for years and years and years now. Hopefully this is automatic. X squared minus 12x plus 35 subtract 8 is now equal to 0. X squared minus 12x plus 27 is equal to 0. Ooh, those are pretty numbers. X minus 3, x minus 9. I did the trial and check method. I checked it. That is correct. So what does that mean? X equals 3, or does x equal 9? Ask yourself. Going back to triple star, can we accept x equals 3? And the answer is no. We must reject x equals 3. We call that an extraneous solution. So I'm going to lightly cross that out. However, you could check that x equals 9 is a solution to the original equation. You could feel free to do that on your own. Sometimes if you don't believe mathematics, go back and plug it in. See if the 9 value here, or the value of 9, makes the original equation true. All right. Why don't we circle that? Once again, we have a final answer, but your work is necessary. So make sure you show all your work that's involved in this problem. Let's solve these equations. There's lots of logarithmic functions here. Whenever you see logarithmic functions, make sure you spot the domain first. So the log base 9 of the argument 4x minus 8 is a function, and that domain has to be what? 4x minus 8 must be positive. So that's going to yield, x must be greater than 2 in this problem. We're going to need that. Let's call that triple star. I'm going to circle that. X must be greater than 2. Well, notice there's a constant on your right. That's just a number. That's a constant. So we could actually use the definition of log right now. So definition of log says this is 9 raised to the exponent. The exponent is log base 9 of 6 is now equal to the argument. The argument is 4x minus 8. Log property on the left says that that pattern is just 6. So this is now equal to 6, and it's equal to 4x minus 8. Nifty. 14 is equal to 4x. X is equal to 7/2. Now, is that greater than 2? It is. 7/2 is greater than 2. It's 3 1/2. So we could circle that as a final answer. And if you don't believe that is the final answer, simply put that back in here and check it. Check to see if it gives you a true statement. Let's look at the second problem. There's once again a logarithmic function. The logarithmic function is the ln of the argument x minus 5. Remember the natural log has base e. Let's state our domain. X must be greater than 5 in this problem. Triple star, and I'm going to circle that. We're going to keep that as a very, very important note. Why don't we get the constant on one side of the equation? Why don't we subtract the natural log of 4 on both sides? And if you do that, you get log properties. This is the natural log of 16 over 4. Ooh, that's nice. Is now equal to the natural log of x minus 5. So that's the natural log of 4 is now equal to the natural log of x minus 5. Now this looks very, very similar to the problem on the left side. Looks like part A. Just remember that natural log has base e. So using the definition of logarithm, we know that there's a little base e here. We know that this is e to the natural log of 4 is now equal to the argument, which is x minus 5. Finally, we have 4 is equal to x minus 5. So x is 9. Is 9 greater than 5? It is. Let's circle that. So, in these problems, yes, you get a final answer, but as usual, make sure you show your work. Make sure you show your logical steps in order, which is what we call work and evidence. The other thing I want to mention is that when you're solving equations, every line of your work is another equation. So notice you started with an equation, you wrote another equation, you wrote another equation, you wrote another equation. Even your answer is an equation. Equation, 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 equation. Make your work consistent. Solving an exponential equation by finding common bases. Now let's give this a try. Whoa, 125, that's a popular number. How can we rewrite 125? Well, there's a big hint here. There's a 5 there. So, knowing your numbers, you know that 125 is simply 5 to the third power. So we replace 125 with 5 to the third, and then we're going to write 2x plus 4 as the exponent on the outside. Technically speaking, probably best to write that in parentheses. This is now equal to what? This is equal to a base 5 raised to the 3x. All right. we continue to simplify. This is a base 5. Now power to the power means multiply the powers. So we get 6x plus 12. 6x plus 12 is now the new exponent on the left side of the equation. On the right side of the equation, it simply says base 5 raised to the 3x. And now we know that exponential functions are one-to-one functions, so we can conclude that the exponents are going to be equal. 3x is equal to negative 12. X equals negative 4. Hmm. 32 and 64. What common base do they share? What numbers do you know? Well, they're both even. In fact, they're both base 2. So why don't we rewrite it? 2 to the 5th power is 32, and then raise that to the exponent negative x minus 4. Over here is equal to, the base is 2, and then raise that to the exponent of 6, because 2 to the 6 is 64. We're getting somewhere here. 2. Next new exponent is negative 5x minus 20 is equal to 2 base 2 raised to the 6. And because base 2 to the x is a one-to-one function, we can now conclude that the exponents are equal. Negative 5x minus 20 is equal to 6. So we get 14 over negative 5. That is in reduced form already, so we could circle that as a final answer. Solve for x in the equation below. We have an exponential function, an odd one, but it is an exponential function, and it's equal to 11. What do we do with this? Let's see. Why don't we get the exponential function on one side of the equation and the constants on the other side of the equation? This is e to the x times e to the 9th is equal to 11. Now we have what? We could balance this equation. We could divide the entire sides by e to the 9th, because e to the 9th is not 0. Now we have the exponential function called e to the x is equal to 11 over e to the 9th. Let's take the natural log of both sides. And on the left-hand side of the equation, we get x. It's now equal to the natural log of 11 over e to the 9th. And you're done. Remember, that is what we call an exact answer. Make sure you find your exact answers first, and if the problem asks you to approximate, you could approximate that on a calculator.